Hi, my name is Nora, and I work with Dr. Kochunov at the University of Maryland. Today I'm here to show you how to calculate an empirical pedigree for use with SOLAR-eclipse software.
SOLAR-eclipse uses a pedigree structure to determine the level of genetic similarity between subjects in a sample. A pedigree is a square matrix n by n, where n is the number of subjects in the sample. The elements in this matrix are called coefficients of relatedness, or kinship coefficients. SOLAR's standard pedigree is computed based on self-reported relationships. For instance, identical twins share 100% of their DNA, and so their coefficient of relatedness is set to 1. Siblings share 50% of their DNA, and so their CR is 0.5. Grandparents and grandchildren share 25% of their DNA, and their CR is 0.25. Unrelated people are assumed to share 0% of their DNA, and their CR is set to 0. However, self-reported values are prone to errors due to misreported relatedness, and seemingly unrelated people may share a significant amount of DNA if they are recruited from the same geographical area. This is known as cryptic relatedness. The errors in the self-reported CR values may undermine your genetic analyses. Therefore, if you have genetic information for your sample, you may consider calculating CR empirically because it may give more accurate estimates of genetic effects. This is called an empirical pedigree. There are multiple ways to calculate relatedness empirically from the genetic scan data. SOLAR provides two approaches. KING, which stands for Kinship for GWAS Studies, also known as the allele sharing approach, and WAC, the weighted allelic correlation approach. The KING approach was developed to verify the self-reported coefficient of relatedness provided by the subjects. It was designed to provide CR values that closely match the self-reported values. The method calculates the coefficient of relatedness between individuals through the following equation, where these are all the heterozygotes for the individuals I and J, and this is the number of heterozygous SNPs that the individuals have altogether. The equation uses identity by descent to calculate how similar the genotypes are through heterozygous and homozygous alleles for the measured SNPs in both individuals. Since the equation looks at homo and heterozygosity for the alleles, it operates under logic operators and eliminates the use of multiplication and division, allowing the calculations to be much faster. This approach has computed CRs that closely resemble the self-reported values. The weighted allelic correlation approach is used for calculating the coefficient of relatedness by looking at the correlation between the allelic scores for each individual's SNPs. This correlation is then weighted by the minor allelic frequency, whether that's proportional, alpha equals 1, unrelated, alpha equals 0, or inversely proportional, alpha equals -1, to the minor allele frequency of the SNP. The alpha parameters allow us to weight your empirical pedigree based on the sharing of common versus rare alleles. Alpha equals 1 assumes that the variant's genetic traits are carried out by common alleles with minor effect sizes. Alpha equals -1 assumes that the variants in genetic traits are carried out by the low-frequency alleles with modest effect sizes. The alpha equals 0 makes your empirical CR independent of the allele frequency. The equation for this method is this, where GIN and GJN are allelic scores for each SNP in the I and J individuals, and PN is the minor allelic frequency for each SNP calculated per sample, and N is the total number of SNPs. Alpha refers to the weighting of the minor allelic frequency relative to SNP. This approach has found CRs lower than self-reported values. Before you create your empirical pedigree, we suggest the following filtering procedure to prepare your genotype file. This is the standard filtering approach that is used by the Enigma collaboration. The full protocol is available here. We suggest that you build your pedigree using only the genotyped data. Building your pedigree using imputed genotypes is not recommended because of the assumptions of genetic similarity that went into the imputation protocol based on the imputation panel. For the most accurate analysis, you should filter out your SNP list to use genetic data that does meet quality control criteria. SNPs for analysis should have a minor allelic frequency less than 0.01, a genotype call rate of less than 95%, and a Hardy-Weinberg equilibrium less than 10 to the -6th power. First, we will go to the directory where we have our genotype files. My directory, Enigma Genetics, has already been made, and it already has all of my genotype files. Please move all of your .bim, .bed, or .fam plink files into the Enigma Genetics directory. Make sure to have the plink and R softwares installed on your computer and be able to utilize a bash shell. These softwares can be downloaded at the listed websites. To check what shell you are using, please type in echo shell. If it is not the bash shell, type bash to switch to the bash shell. Once you are finished with the filtering, you may return to your previous command shell by typing in exit. Before you begin the filtering, please make sure that you are the or one of the owners of the Plink files in the folder. The files should have readable permissions, and the folder should have readable and writable permissions under your ownership. To filter the SNPs from your data, input the following into your computer's bash terminal. Export data file raw, and this should equal to the base file name without the extension of your genotype information files. Make sure to not have any spaces around your equal sign or you will end up with an error. Next, we're going to write the pathway to our Plink executable file. And then these arguments. And then I'm going to add in this argument non-founders because my dataset does not have any founders, which affects the SNPs being tested through the allelic frequency test. And this is how you can find out whether or not you have any founders. When it runs the analysis, it tells you, and since I have 0 founders, it would have taken out all of the SNPs from my list. Since I have 1,142 non-founders, I had to put in this argument to prevent all the SNPs from being filtered out. And all of our output files that are filtered SNPs will come in through this external output. So data file raw was my genotype file base name, all CHR, and it will come out all CHR underscore filtered, again in Plink file format, .bed, .bim, and .fam. So as I said before, all of the information will be written to all CHR filter.fam, .bim, and .bed, which is right here if we look. So now we're going to merge the raw genotype data with the SNPs that have been filtered to avoid processing genetic data for SNPs that do not meet the quality controlled criteria. So now we're going to type in export data file equals, again, no spaces, data file raw score filtered, and then we're going to type sudo awk and then your base file name .bim, so in my case, and then it goes to a new file it'll create, which you are going to do your base file name .snplist.txt. Now that that's written right there, we're going to again do the pathway to our Plink executable. And then p file, data file, extract, our base file name again .snp.list, snplist.txt, make web, no web, out, and local, which will create files called local. So now we're going to type some more arguments in, which I will fast forward through for your sake. Now our final argument for filtering the SNPs will be, again, the pathway, and at this point I think you've noticed that I'm not putting in no founders anymore. You only need to do that for the initial filtering. After that, you don't need to put that in again. And then again, your base file name, so in my case, all_chr.smp list. And external will be all of the filtered Plink files we will be using for the empirical pedigree creation. Okay. Now, we have all of these external files, external.bed, .bim, and .fam. And these will be the files we're going to be using for our empirical pedigree formation. So in my case, I'm going to start Solar, and then I'm going to put in my arguments. So now that our analysis is done, we can see that we have our king pedigree file. Now furthermore, if we want to make separate pedigrees for each chromosome that you have in your Plink file, you would just add per chromo as an argument before your output argument, like this. So same old, but you add per chromo right here, and you go ahead and run your analysis. Your output file will now have the chromosome number appended to the end of its name, so you'll know which chromosome you are looking at. Now we're going to cover the correlation pedigrees. We're going to use the same command as for the allele sharing pedigree, but we're going to add in the argument correlation and an alpha integer before the output. So the alpha integer you choose can be either positive or negative. Similar to the WAC directories, we're going to use -1, 0, and 1. So here we're going to do the correlation pedigree analysis. We're going to type in So now that the analysis has finished, we should be able to see And there you have it. You can now make average allele sharing and correlation empirical pedigree files using SOLAR-eclipse. Thank you so much for watching.